Today's topic is part of Unit 1, Number Systems, and we'll be talking about roots, rationalization, and exponents. Okay, so our other video on Unit 1 number systems was the introduction to real numbers and representation systems. So today we'll be talking about the other part of the unit, which is roots, rationalization, and exponents. So the learning targets. At the end of the video, you will be able to understand the meaning of an nth root of a real number and express roots using exponent notation, rationalize denominators of expressions that contain square roots using conjugates, apply the law of exponents to simplify expressions, and finally use exponent rules to rewrite expressions in simpler algebraic forms. Now let's move on to the concept of an nth root. So the definition is a number x is called the nth root of a real number given by a if x to the power of n or x raised to n is equal to a. So essentially, the nth root is a number that, when multiplied by itself n times, equals a real number. So, for example, we can represent the square root of 9, the cube root of 8, and the fourth root of 16 as nth roots, where the square root of 9 is equal to 3, the cube root of 8 is equal to 2, and the fourth root of 16 is equal to 2. And on the right side, we can see that 3 is the nth root of 9, where n equals 2. So 3 is the second root of 9. 2 is the third root of 8, and 2 is the fourth root of 16. So here is some notation on nth roots, which we'll look at later. But we can represent, for example, the square root of a as a to the power of 1 over 2. And we can represent similarly the third root or the cube root of a as a to the power of 1 over 3. And similarly, we can represent the fourth root of a as a to the power of 1 over 4. So in general, we can represent the nth root of a as a to the power of 1 over n. So this notation will help us connect roots with the law of exponents, which we will see shortly. So here is a visual understanding of roots. So we can say that the square root of a number is splitting its area. So in the picture here, we can see the square root of 9 blocks will be splitting it into 3 because 3 to the power of 2 is 9. Similarly, since squares involve area, the cube root is splitting volume. And in general, the general root of any real number can be said to be repeated grouping. So to build intuition, a square root represents the side of a square with area A. A cube root, or the third root, represents the side of a cube with volume A. And the nth root represents repeated equal grouping n times. So for example, if a question asks the third root of 27, we can think of the question as, what number multiplied by itself 3 times gives 27? And in that case, the answer is 3. Now let's talk about rationalization, which is a very common requirement and practice in algebra. So simply, rationalization is where we remove all irrational numbers from the denominator of an expression. The reason we do this is because expressions that have irrational denominators are harder to calculate, harder to compare, or harder to further simplify. To perform rationalization, we use conjugates. And the conjugates is simply the negated version of an expression. For example, if we have the expression a plus b times the square root of x, we can say its conjugate is a minus b times the square root of x. And similarly, the square root of x plus the square root of y has the conjugate of the square root of x minus the square root of y. So multiplying conjugates together uses the identity that a plus b times a minus b equals a squared minus b squared. And what we're doing here is eliminating the square root from the expression completely. So here's an example of rationalization. So let's rationalize 1 over or 1 divided by 3 plus 2 times the square root of 5. So we can tell from the previous slide that 3 plus 2 times the square root of 5 is in the form of a plus b square root x. So we can form its conjugate by negating or making the square root term negative. So we'll take our original expression, 1 over 3 plus 2 square root 5, and multiply both the numerator, or the top, and the denominator, or the bottom, by the conjugate, which in this case is 3 minus 2 times square root 5. So when we multiply the numerator, it is simply that expression, the conjugate, times 1, which is just itself. However, the denominator now becomes the case or the identity that we just talked about, where we have 3 plus 2 square root 5 times its conjugate, or 3 minus 2 square root 5. So essentially, we get rid of the square root here, and by multiplying the two expressions, we get 3 squared, or 3 to the power of 2, minus 2 square root 5 all squared. And if you evaluate that out, you'll get 9 minus 20 equals negative 11. So we can write our final answer as 3 minus 2 square root 5 all over negative 11. And that is a rationalization of our original expression up in red. So we've successfully removed the root from the denominator. Now, all we have on the bottom is a number that is easy to work with, which in this case is negative 11. So now let's revisit the law of exponents, which you have already studied in previous classes, but we now will apply them to real numbers. So there are several laws or identities. The first one is where we multiply powers with the same base. Remember, the base is a number being raised. So in this case, the base is the real number represented by a. So a to the power of m times a to the power of n equals a to the power of m plus n. So when we multiply powers with the same base, we just add the powers together. And similarly for division, we subtract the powers. So a to the power of m divided by a to the power of n is simply a to the power of m minus n. The third one is the power of a power. So if we raise a to the power of m all raised to n, we simply multiply the powers together. So our expression is now a to the power of m times n, or just mn. The fourth one applies in all cases. So any number a raised to the 0th power, so a to the power of 0, is always going to equal 1. And lastly is negative exponents. Now it's important to note that a number raised to a negative exponent is not negative itself. The final answer will still be positive because a raised to negative n, or a to the power of negative n, is simply the reciprocal of a to the power of n. And remember, the reciprocal of a number, which we discussed last video, is 1 divided by, or 1 over, a to the power of n. So these rules hold for integers and also form the basis for rational exponents that we will see in the next slide. So now we will extend the laws of exponents to rational exponents, which is specifically mentioned in the syllabus. So, number 1, when we have a real number a raised to the power of a fraction, say p divided by q, our expression is simply the qth root of a raised to p. And our second one is that a raised to the power of 1 divided by n is simply just the nth root of a. So here are some examples. So 27 raised to the power of 1 divided by 3. Well, we can simply say that this is the qth root of a all raised to p. And in this case, q is equal to 3 and p is equal to 1. So the qth root of a, or the third root of 27, can simply be written in this form, and all raised to the power of p, which in this case is just 1, which doesn't change our expression at all. So the cube root of 27, or the third root of 27, is equal to 3. And secondly, 16 to the power of 3 divided by 4. So in a similar fashion, we can take the qth root of a raised to the power of p. In this case, q is equal to 4 and p is equal to 3. So we can raise the fourth root of 16 all to the power of 3. So in this case, the fourth root of 16 is 2, and 2 to the power of 3 equals 8. So today we covered our second topic, which was roots, rationalization, and exponents. So today we learned what the nth roots of real numbers are and how to interpret them. We also learned how to rationalize expressions that contain square roots in the denominator using conjugates. And finally, we learned the full set of the laws of exponents, including how to work with rational exponents. And these are all ideas that will work together to form the foundation of real numbers. And you'll use all of these skills in algebra, trigonometry, calculus, and other classes as you progress in mathematics. So thank you for listening today, and I hope that you learned something.